Functional connectivity gradients provide us with a way to display the flow of information in the brain. Previous studies using this technique show that the mouse brain prioritizes sensory information, and that sensory information is translated and integrated into higher-order cortical regions, process for which the thalamus plays a key role. Here we used a task that involves higher cortical activity, the go-no-go task, to understand whether there would be different thalamocortical dynamics in go-no-go conditions of a sensory motor task. In order to assess this question, we used one recording session of this 10 minutes dataset. We took the correct trials in which visual stimuli and motor response were to the left and correct no-go trials. This subset contained 250 milliseconds long recordings from 698 channels that corresponded to neurons in two thalamic nuclei, the lateral hypothalamus, some hippocampal subfields, visual cortices, frontal areas, and these neurons are arranged in a manner that we expected the information to flow. After trying to use the raw data, we decided there was not enough time to make it work. Then we explored on how to smooth the spiking data using splines and low filters, but saw that this wasn't done usually in this kind of data, so we decided not to use it. The analysis consisted on principal component analysis to identify low-dimensional temporal gradients, exploration of the differences in the dynamics in the first principal component for the left and no-go trials, also a cross-correlation of the spikes in all neurons, as it's shown here, and an autoregressive model of a few neurons with a lack of one.
So in order to observe the functional connectivity gradients, we perform principal components analysis. So ideally, we would obtain the principal components from the analysis and project them onto a 3D brain space, such as the Allen Brain Atlas. However, due to time constraints, we decided to just map the principal components onto a 2D space. So here is our 2D brain space we created, sorting all the neurons according to the brain areas, such as the thalamus and the other cortical areas. And the unknown areas are just the unidentified areas. So we perform principal components analysis on the left-go trials. And what we see is that the hippocampal area and the thalamus seem to have the largest weights for the principal components. So we performed the same analysis for the no-go trials, and we see the same brain areas having large weights. So we wanted to see which brain areas were highly correlated. So we performed a cross-correlation neuron by neuron for 698 neurons. And these neurons are sorted according to their brain areas. So we wanted to compare the left-go cross-correlation with the no-go cross-correlation. And what we saw is that the areas that are highly correlated in the left-go cross-correlation are also highly correlated in the no-go cross-correlation.
Let's look closer at the principal functional connectivity gradient with the function of time. Here we have plotted every 50 millisecond time beam for all the trials for the no-go and for the left-go. No-go means when mouse doesn't move the wheel, and left-go means when mouse move the wheel. And in the no-go trial, you see these different blocks. So the top blocks represents thalamus and its specific nuclei, and all other blocks represent different cortical areas. For example, specific areas in hippocampus, visual cortex, and non-visual areas. And now I will play the movie, so you will see how different areas in the thalamus and in the cortex come in play during the no-go and left-go task. And we can learn a lot of interesting things from these dynamic functional connectivity gradients, but I want to highlight only two important things that as we go higher with the time, for example, so you see here no-go trial, and you see the suppression in the visual, in the visual and in hippocampal areas, and here in contrary you see excitation in the visual areas in the left-go trial. And that is extremely interesting because you also see the same time suppression in the thalamus for no-go trial and other way around in the left-go trial. And this is very interesting because in the no-go task, mouse should not move the wheel after having a visual stimuli in the center. But in the left go, after looking at left stimuli, mouse need to move the wheel. So that's why the visual areas and also different thalamic nuclei need an integration and also execute the motor command. And that's really fascinating. The summer school was great. I super enjoyed specifically well-crafted Python notebooks and also interactive discussion with TA and also other colleagues and breakout rooms. And it was fascinating. And I hope all other neuroscience summer school organizers learn from this beautiful experience.